Fine. What am I going to do next? I'm going to say, well, if I'm hoping that I can do replication, then this has to be equal. I'm looking for a portfolio such that this dx expression is equal to the dc expression. I'm looking for a replicating portfolio. I'm looking for a portfolio. This is for any portfolio, but I'm going to try to find one for which this expression is exactly equal to this expression. And I have to have replication at the very end. At the very end, I want to have the portfolio equal to the value of the option. But let's first do it before the very end. I'm just going to do it for every t before maturity. The way I'm going to do that, I'm going to make this part, the dt part here, equal to the dt part here, and then also this dw coefficient here equal to this dw coefficient here. If I can do that, then they will be equal. If I make this dt term equal to the dt term and the dw term equal to the dw term, then they will be equal. Let's first do the easier thing. Let's make this, try to make this equal to this. Sigma and sigma will cancel, and I will get that pi has to be equal to SCS. Okay? It gives me an expression for how much money I should hold in stock. If I divide by S, what I just told you is pi over S has to be equal to CS of t at S of t. What is the left-hand side? The left-hand side is, as we already mentioned, the number of shares. And we get this famous result in continuous time Black-Scholes pricing and replication, that so-called delta of the option, which is the number of shares. Well, the delta of the option is actually defined to be this right-hand side. It's the derivative of the option price with respect to the underlying. Partial derivative of the option price as a function of the underlying, and the derivative with respect to the underlying. That's called the delta of the option. That's exactly how many shares you should hold if you have a hope of replicating your option. Okay? The number of shares has to be equal to the delta of the option, meaning to the first derivative of the option price with respect to the underlying. Fine. Now when I know that, I'm going to compare the dt terms, try to make them equal. Let's try to make this equal to this, but using that pi is equal to SCS. So instead of pi, I'm going to write SCS. And then instead of x, I'm going to write c, because I want x to be equal to c. I want replication. So write c here, and write SCS here. First thing to note is mu term will cancel. I have mu SCS here, I will have mu SCS here. When I make these two guys equal, that will cancel. Mu disappears, which is fantastic. This is one of the reasons why Black and Scholes pricing theory was really very fast, very quickly applied in practice, because you don't need mu in this model to price options. And mu, which is the return rate of the stock, is very hard to estimate. Whether a stock returns on average 10%, 5%, and minus 3% a year, it's very hard to estimate. What you need is R and sigma, which are easier to deal with and estimate. Okay, so mu term will cancel, and the rest I make this equal to this. Let's see how it looks like. If you just make those two things equal, move everything to one side and leave 0 on the other side, you will get this. What is this? This is an expression which tells you that the function c and some of its partial derivatives, partial derivative with respect to t, partial derivatives with respect to stock, and the second and first times some coefficients, and times s squared here has to be 0, and this has to be 0 for every t and every s. Okay? Well, for every t positive and every s positive in this model, and time is positive and s is positive, so for every t s greater than 0, well, t in fact we only need it up to maturity, t less or equal to t, capital T. And then at capital T there is also boundary condition. We want replication also at capital T. At capital T, no matter what the stock price is, I want the contract to pay the value of the, I know what the value of the claim has to be. It has to be equal to G of S, no matter what S is. Okay. This equation here is a partial differential equation. It's just, which means it's an equation about involving a function and its partial derivatives. Okay, so if our conjecture is correct, that we can in fact replicate C of t s of t for some function c, and that function ends up paying exactly how much the claim pays, no matter what the stock price is. Okay, if we have any hope of replicating this, it has to be the case that that function has to satisfy this. Another way around, if we find a function which satisfies this, then by what we did in the previous slide, that function can be replicated if it satisfies this by this portfolio, which satisfies this. And because it can be replicated and it ends up with a payoff equal to the payoff of the claim, that function has to be the price. It's the cost of replication. It's equal to the value of the wealth you need to have at each time to replicate at the end. It has to be the price. It's the cost of replication. Okay? Same logic that we used for pricing since the beginning of the course, also here. But it's characterized, the price is characterized as a solution to partial differential equation. This was published, as I said, in 1973. It happened by chance that that was the same year when the first stock option exchange was opened in the world, in Chicago. And option traders pretty quickly realized they can use this to price options when they or get an idea what the value of options should be when they trade them. It was really one of the most successful. It is one of the most successful stories in terms of very fast application of high theory in finance or economics into practice. And maybe the most successful example, especially in the beginning, it was successful in the sense that for the first 10-15 years, it was kind of a self-fulfilling prophecy. Okay, the model was correct because everybody was using it, and everybody was using it because it was correct. So until a crash in 1987, mostly this model was used for pricing options, and because everybody was using it, it seemed fine. Even though even if stocks don't really behave like a log normal distribution or a geometric Brownian motion is the name for this process, the stochastic process. If everybody using the Black-Scholes formula for options, options will look like they follow the theory. Then there was a crash in 1987, and people started thinking more seriously about. They realized maybe this is not a perfect model, and maybe there are ways to improve it, which those ways we'll talk about later. But going back to 1973, this is what Black and Scholes did. Still not finished, I didn't give you the formula, but before I do that, let me just say, this is not exactly how they did it. The way they did it, if you read their paper, they, instead of replicating the option value by trading in the stock and the bank, they really tried to replicate the bank the risk-free asset by trading in the stock and the option. Okay, they found a strategy which would eliminate the risk by trading in the stock and the option. You eliminate the risk, meaning and then by no arbitrage, if you eliminate the risk, that strategy has to be equal to holding money in the bank. So effectively, they replicated the bank account by the option and the stock. But it's the same thing. They got the same differential equation, whether you're replicating the option with the stock and the bank account, or the bank account with the stock and the option. Pretty much, it's the same thing. But for educational purposes, it is better for us to think in terms of replicating the option rather than replicating other assets. Right, to recap these two slides, what Black and Scholes did, they knew about Ito's rule. Ito's rule wasn't that that old at that time. It was, about 30 years old or less. But they knew about it. They knew about the model. They suggested to work in this model to price options, and they had this idea of trying to, if you want to replicate the bank account, I don't think they used that terminology, but to kill the risk with trading in the option and stock, and they came up with this partial differential equation. And then they concentrated on the call option. So for this function g of s, they took it to be the call option. It turns out that for the call option, this partial differential equation has a solution. It has in fact, a unique solution if you are careful about boundary conditions. It has a unique solution, which then, so everything works. Our conjecture works that this can be replicated, and that solution is smooth enough to have these derivatives, even though at the end the call option is not differentiable, not to mention twice differentiable at the strike price. It has a kink. However, before maturity, all of these derivatives exist. And that's their famous formula. It's the formula for the solution of this partial differential equation with the boundary condition where the g of s is the call option payoff. The partial differential equation is always the same. For every g of s, the solution changes because you change the boundary condition, this terminal condition at maturity. Let's look at the formula. I'll give you the formula. I guess in the next slide, this is just repeating what I've said. It has a unique solution, which means that everything works. We can replicate the option by holding delta shares at each time, and therefore the option price at time t is given by this function c of t and s. And the mean return rate, mu, doesn't influence the option price. All right. The one thing maybe that I should also emphasize is this partial differential equation, there is no randomness in it. This is a completely deterministic animal.